Hello friends, welcome to chemistry classes by Vijay Kumar Sethi. In unit 4 class 12 we will discuss about the chemical kinetics, and in this video we will discuss about the average in instantaneous rate of reaction and units of rate of a reaction. But before it we will discuss what is chemical kinetics. For a chemical reaction, scientists or chemists try to find out three things. First one is feasibility, that is spontaneity of a chemical reaction, which can be predicted by the thermodynamics. As we have discussed, if delta G is negative or zero, then reaction is feasible or spontaneous. Second thing is extent to which a reaction will proceed can be determined from the chemical equilibrium, that is magnitude of K. Third thing is speed of reaction, that is time taken by a reaction to reach equilibrium, and this is determined by chemical kinetics. So we can say what is chemical kinetics? This is a branch of chemistry which deals with the study of reaction rates, factors affecting reaction rate and their mechanism. This is called chemical kinetics. And on the basis of rate of reaction, chemical reactions can be classified in the three categories. First one is reactions which occur instantaneously, that is instant reaction. Like precipitation of silver chloride occurs instantaneously by mixing of aqueous solutions of silver nitrate and sodium chloride. These are instant reactions. Reactions which occur very slow, like rusting of iron in the presence of air and moisture. Next one is reactions which occur with moderate rates, like inversion of cane sugar and hydrolysis of starch. Clear? Now see, what is the meaning of rate of a chemical reaction? This is defined as the change in concentration of a reactant or product in unit time. If we consider one hypothetical reaction, in this reactant is represented by R, converting the product which are represented by P. Now at time T1, the concentration of reactant is R1, concentration of product is P1. And at time T2, concentration of reactant is R2 and concentration of product is P2. Again remember, if we put the symbol or formula of any species in the square bracket, then it represents the concentration. Then we can say change in time, that is delta T is equal to T2 minus T1. Change in the concentration of reactant, that is delta R is given by R2 minus R1. Change in the concentration of product, that is delta P is equal to P2 minus P1. Then according to the definition of reaction rate or rate of reaction, we can say change in concentration of reactant divided by time taken for change. Now the concentration of reactant is changed, and that is this is delta R. Again remember, this delta R is negative. How this is negative? As the reaction proceeds, concentration of reactant is decreased. That's why we can say this R2 is less than R1. That's why difference of these two, that is delta R, is negative. That's why this term is negative, and this is divided by delta T, that is change in time. Then this will come negative, but rate of reaction will never be negative. That's why this factor is multiplied by minus 1. This is the significance of this minus, and actually this is an average rate. Clear? Since delta R is a negative quantity, as concentration of reactants is decreasing, it is multiplied with minus 1 to make the reaction a positive quantity. Clear? Then rate of reaction in terms of product, we can say this is the change in concentration of product divided by time taken for change, and that's why this is delta P divided by delta T, and this delta P is always positive because as the reaction proceeds, concentration of product will increase. Okay, and this is again an average rate. Okay, then average rate depends upon the change in concentration of reactants on products and the time taken for that change to occur. Okay, now next one is instantaneous rate. Instant, that is at a moment, at a particular moment. Before we discuss this instantaneous rate in terms of a chemical reaction, we will discuss the one common phenomena, that is speed of any vehicle. Speed of any vehicle. If we go from one place, for this place is X, and we have to reach up to the place Y. Yeah, and the distance between these X and Y, and this is, suppose this is 150 kilometer. And the time required to cover this distance is 3 hours. If we divide this one, that is 150 divided by 3, and this will come, that is 50 kilometer per hour, and we can say this is our average speed of the vehicle. Okay, now but vehicle is not running with this speed at every time. The speed sometime it may be 80 kilometer per hour, or it may be zero when there is an exam is there. Clear? That's why we will take the average. But if we find out what is the rate, what is the speed of a reaction at a particular instant, then what we will do? We will see in the speedometer. Clear? And then that rate at a particular instant in a speedometer, that speed in a speedometer, that gives the instantaneous speed. Okay. In the same way, we can find out the instantaneous rate of reaction, that is rate of reaction at a particular moment of time. Or if we can say it is the average rate at the smallest time interval, say dt. Again read dt. Actually, this delta represents the change. Clear? But if this delta t is approaches to 0, we can say when this change is very small, then this is represented as dt. So we can represent mathematically instantaneous rate like this is minus delta r divided by delta t, and this delta t approaches to 0. This represents the instantaneous rate in terms of concentration of reactant. In the same way, rate is equal to delta p divided by delta t, and this delta t approaches to 0. Clear? And this we can also represent instantaneous rate is equal to dr divided by dt. What d is small, very small interval of time or very small change in the concentration. dp divided by dt. Now, how can we determine this instantaneous rate? It can be determined graphically by drawing a tangent a times t on either of the curves for concentration of r or p versus time t and calculating its slope. Now, just see how can we plot these graphs. Now, see this is between concentration of reactant versus time. Initially, concentration of reactant is maximum. This is represented by R naught, R0 or R naught. As the reaction proceeds, concentration of reactant is decreases. Okay. As the time is proceed, concentration of reactant is decreases. Now, if we see at suppose time t1, the concentration of reactant, this one, that is this is R1. And at time t2, concentration of reactant, that is given by R2, and difference of these two we can find out the average rate, it is delta R divided by delta T, and we already discussed why this is multiplied by negative sign. Okay, but if you find out the rate of a reaction at a particular time, that is T. Clear? This is particular time T, then this is the particular time, and we draw this tangent. This is the tangent, okay, at this point. And if you find out the slope of this tangent is this divided by this. Okay, this will be the slope. Clear? And again, why this is negative? Because this term is in negative. In this way, we can find out the instantaneous rate. In terms of change in concentration of product, we can say this is the concentration of product and this is time. Again, initially concentration in product is 0. As the reaction proceeds, concentration of product is increases continuously. And again, at time t1, if concentration of product is p1, at time t2, concentration of product is p2, then we can find out the average rate by using this formula. But if you want to find out the instantaneous rate at a particular time t, clear? Then at this time we draw this tangent. This is the tangent, and the slope of this tangent, this is this dp divided by dt. This will give the instantaneous rate. In this way, we can find out the instantaneous rate by using this graph. Okay. Now see, what is the units of rate of a reaction? Actually, units of rate are concentration divided by time. Clear? Concentration time inverse. If concentration is expressed in mole per liter and time is in second, then we can say unit of rate of reaction is mole per liter per second, or we can also say mole liter inverse second inverse. In a gaseous reactions, when the concentration of a gas is expressed in terms of their partial pressure, Clear? And partial pressure, unit of partial pressure is either bar or ATM. Then we can say that is ATM second inverse if time in second, or bar second inverse. Now consider one equation, Hg plus Cl2 gives HgCl2. Now again, see this equation carefully. In this case, stoichiometric coefficient. What are the stoichiometric coefficient? That is this. Number of reactants and products. This will give the stoichiometric coefficient. Nothing is written, it means 1. In this case, the stoichiometric coefficient of each reactant and product is same, and that is 1. Okay. Then we can say rate of reaction is this. It can be represented either in terms of concentration of reactant or in terms of concentration of product. Okay, this is why this is minus, because this is the reactant, concentration of reactant is decreasing. That's why delta Hg divided by delta T is equal to minus delta Cl2 divided by delta T, and this is equal to delta HgCl2 divided by delta T. Clear? Now we can say that is rate of disappearance of any of the reactant is same as the rate of appearance of the product, because the stoichiometric coefficient of all the reactants in product is same. But if this stoichiometric coefficient is not same, then what will happen? And how can we express the rate of reaction? See this one equation. In this case, 2 moles of Hi decomposes to produce 1 mole each of H2 and I2. Like see, 2Hi gives H2 plus I2. Now what is the meaning of this? We can say when 2 mole of Hi will decompose, it produce 1 mole of H2 and 1 mole of I2 in the same time of interval. It means rate of disappearance of Hi is twice the rate of appearance of H2 and I2. Okay. Since rate of consumption of Hi is twice the rate of formation of H2 or I2, to make them equal, what we will do? Term delta Hi is divided by 2. Why this is 2? Because this 2 is the stoichiometric coefficient of Hi. Then we can say rate of reaction can be represented like this. This is equal to minus 1 by 2 delta Hi divided by delta T. This is equal to delta H2 divided by delta T, and this is equal to delta I2 divided by delta T. I think it is clear. If stoichiometric coefficients are different, then how can we express the rate of reaction? Rate of such a reaction where stoichiometric coefficients of reactants and products are not equal to 1, rate of disappearance of any of the reactants or the rate of appearance of products is divided by their respective stoichiometric coefficients. Clear? Now see one more example. This is the example. 5 Br minus plus BrO3 minus plus 6H plus gives 3 Br2 plus 3H2. If we want to express the rate of reaction in terms of each reactant and product, now CK, rate is equal to minus 1 by 5. Why this is 5? This is the stoichiometric coefficient of Br. In the same way, this is delta BrO3 divided by delta T. Its stoichiometric coefficient is 1, and it is not necessary to mention 1. Now this is in terms of change in concentration of H plus, this is 1 by 6, because this 6 is the stoichiometric coefficient of H plus. In the same way, equal to 1 by 3 delta Br2 divided by delta T, and this is equal to 1 by 3 delta H2O divided by delta T. If gaseous reactions are there, then for a gaseous reaction at constant temperature, concentration is directly proportional to the partial pressure of a species, and hence rate can also be expressed as a rate of change in partial pressure of the reactant or the product. Is it clear? Thank you.